Hi, good afternoon or good morning, everyone. This is Celso Batalha, Astronomy 10. It's a pleasure to be with you again after 1 week of exams, and I hope you guys did well. I checked the grades. The grades were at the bullseye, and and at least in the average that I was expect the class to get. As you found out, uh, the exams are consist on questions that require an understanding of the subject. Although I know you can have your open book, you can go to Wikipedia, but you have to know the subject to answer some of the questions that require a little bit of a critical thinking. Also, I would like to emphasize the discussion we are doing this week, and and I'm pretty sure some of you have already posted your comments on the tools of astronomers. So exactly why astronomy is a scientific enterprise, although contrary to the other sciences, we do not bring pieces of what we are studying to our lab. I mean, we don't bring pieces of quasars, galaxies, and black holes to our laboratory to validate their existence. Exactly what we use light. So the light, as it interacts with matter, it, it establishes fingerprints that as we detect using telescope, we can read out and we can then infer the properties of the gas where that light interact, which means gas has the property of not only produce light, but also to absorb light and also to scatter light. Hey Tor, getting you there. And now I'm going on my monologue. I can hear you. Now you might be able to see me.
Yeah, I can see you now.
Yeah. Um, but you don't want to be seeing my face, so I'm gonna. But I was going on my monologue talking about the tools of astronomers, spectroscopy, and photometry. And for this week, the seed I would like you um, to discuss is with respect to the subject of this week class, which is, let me see if I can share my screen now. Just a moment. Now I'm sharing my screen. Is about other worlds, an introduction to the solar system. So, in fact, when we think about this week's subject, which is the solar system, and so we are going to see planet Earth as a planet, not just as our home planet, but just another planet. And as we dive into other worlds in our solar system, why not to discuss other worlds out there? And and the idea, the seed for this coming week discussion is how astronomers have used photometry and spectroscopy to find other worlds out there, which means planets that circle stars other than our sun, and they are called exoplanets. So make a clear description what were the techniques used or employed, in fact, spectroscopy and photometry, and how these two techniques, how these fundamental tools of the astronomers could be used together to um, to provide over thousands of planets confirmed out there in circling other stars. To help your aid on this subject, here's what I would like you to check. check this out. Everything you need to know is right here.
Of nachos. A whole new world. That's what we'll see. That's what we'll see. I'm looking for one tug, pull the planet, one tell, a wobbling sun. I've searched for years, haven't found a one. They're out there. One jump in radio redshift, one slip, spectral lines. They'll see if I can show them the signs. Pistache.
Green men.
Take 5, take 10. Just a little cash, guys. I can take a hint, better face the facts. Second hand will have to do.
So I'm gonna put this on canvas. It's 8 minutes, but gives a nice history of the exoplanet. Since 1990, you know, all the attempts astronomers made since that time to find planets, and their effort resulted in no planets they couldn't find. And then the technique was improved with spectroscopy, and then they confirm a candidate, and then we have another technique, photometry, being used, and now we have thousands of planets. This is a fun link, and I would like you to not only explain how these two tools, spectroscopy and photometry, combined helped astronomers to determine the existence of several, in fact, thousands of exoplanets out there. They seem to be more populated than the stars we have in our galaxy, but also bring me some, in continuation to the seed discussion, so photometry, spectroscopy, and the search of exoplanets, how these techniques are employed, and bring me one technical information from this video, from this link, a cappella. And in fact, yeah, there are several, but you bring me just one and tell me your understanding of it. So 3 things: photometry and spectroscopy on the search of exoplanets, how these techniques are used to help astronomers to confirm the existence of exoplanets, but also bring me a technical issue that is displayed, that is shown in this link. Okay, and I will put this in Canvas. Briefly over the other worlds. So chapter 7. Oh, by the way, the homeworks, they kind of I was not able to pair the homeworks test banks with the chapters. So you might find some questions that are not exactly listed in the book. But, you know, since I will open homeworks again towards the end of semester, so we are basically hitting the midpoint. So we have another 2 months or 3 months or so to go. So in the last month of this term, I will open the homeworks again, not the discussions or not the Astro News, but and by doing so, I would like you to review the homeworks and try to improve on them. But basically, our solar system consists of a sun. You have 8 major planets, 4 terrestrial planets. They are rocky type of planets, and Earth is one of it, and 4 gas-like giant planets, so we have 8 planets, and there are dwarf planets. Pluto is one of it. Haumea is one, another. Makes another one. So there are several dwarf planets. They orbit the sun, but they are not considered planets. So New Horizons is one of the missions that is out there exploring our solar system and is bringing, in fact, fantastic science with respect to Pluto. Cassini showed Saturn with abundance of detail as none in the past had shown. So asteroids are rocky type of objects that can be found in between Mars and Jupiter, and they look like planetesimals, which are rocky type materials that were formed out of accretion in the solar nebula when the solar system was basically forming. So the sun or the solar system and stars out there were formed out of gas and dust that exists in the interstellar medium, and gravity pulled the gas into a center of gravity where most of the gas will reside, and then a star will be located at that point. And some leftover material, not a lot, is 1/100th as far as mass is concerned of that original mass, ended up encircling the star in a plane pretty much coinciding with its equatorial plane, and eventually gas slowly falls and migrates into the star, and we call that process of falling, we call that accretion. So out of this material in the circumstellar disk, then planets and satellites and asteroids and comets happen to be formed. And here's an example of comets. How these so-called first objects grew to be formed out of accretion, like the same process by which snowflakes happen to be formed in our atmosphere. So one molecule at a time, or one atom at a time, these crystals grows, the grains grows, and eventually static energy just glue them together, and they grow in size. And in a few million years, they are pretty much what we call planetesimals. That they can reach significant size. Now, comets are also some of these leftovers. In fact, they were formed further out in regions where the concentration of volatiles are larger than it is on terrestrial or metal type of compounds, and then comets are therefore formed. So how can we measure, how can we date material in the solar system? First, if we collect, we can do radioactive decay and radiometric measurements with this material. So some atoms are unstable and they spend some amount of time, it's called half-life, to reduce its sample to in half. In elements we call daughter elements. So once you know these crystals were formed with these unstable atoms, if you collect them and then you count how many of the parents and daughter ratios are, you can estimate the age with significant precision of your sample, as long as you don't have a lot of transmission and diffusion going on in your sample, which might masquerade your results. But it's a sufficiently strong and robust technique. Now, Earth is, in chapter 8, it focuses on our planet. So Earth as a planet that is one of the few geologically active objects in our solar system. So Earth, and because of the propagation of waves and seismic waves, we know Earth is divided in an inner core and an outer core. So the inner core has a solid structure, and the outer core has a liquid characteristics, and the mantle is made of solid rocks. And the liquid part of the core is the one that generates the global magnetic field that we know and we can measure in our planet. As the planet rotates and as this liquid mantle is comprised of some ionized material, as Earth rotates, this particle circulation generates a global magnetic field. So you could say the interior part of Earth is divided in an inner core, an outer core, and then the mantle and the crust. The crust is where we live. And how do we know of these different regions? Because of seismic waves. In the beginning of this chat room, I was mentioning light as and the interaction of light with matter as the one responsible for bringing us information about the universe out there. As light interacts with the atmosphere of stars, or as light interacts with the gas that surrounds galactic halo, then we get to know what these environments are because of the signatures the light brings with it. Now, life doesn't propagate through Earth's interior because it's opaque, but seismic waves do. And in a similar way, if an earthquake occurs on Earth, or if somebody explodes some missile somewhere, seismic waves will be generated and captured in other regions of Earth's surface, and by doing so, geologists can map the interior part of Earth to reconstruct what the interior part of Earth is based on the arrival states of these waves. So we don't need to collect a sample or go inside Earth to find out what Earth is made of. I was mentioning the magnetic field that's surrounding Earth, and here's a display of it. This magnetic field is generated by first Earth rotation, second by circulation of this ionized material in the liquid part of Earth. So Earth, and more particularly the lithosphere, the topmost part, the one that happens to be on top of mantle, is brittle and is in fact is made of several plates that are broken in very specific places. And these plates, they have their own independent movement. In some places, as indicated in these black arrows, these plates are moving apart from one another. In other areas, like here in California, San Andreas, the plates are moving past one another. And in some other regions, the plates are colliding with one another, like I'm indicating right here. This activity is caused and is driven by energy generated in the mantle. So if we go back to this picture here, the mantle, which lies between the core and the lithosphere, the mantle is made of rocks, is solid, but is not brittle. So this solid material can circulate, and it does circulate like in a convective mode, in the same way that ice that is placed under high stress level, ice can move like it does in glaciers. And this ice motion does things, carved mountains, carved valleys, and also stretches and scrapes mountains. So plate tectonics is a theory first envisioned by Alfred Wegener. So Alfred Wegener, in fact, he didn't invent plate tectonics, but he suggested that Earth was divided in plates, and these plates somehow moved apart and had their own motion. And the way he proposed that was, if you look at South America, this curve in South America, it kind of matched the curve in the west coast of Africa, as if you think in a jigsaw puzzle, you could just bring the South American and snuggle it with African continent. And the same way, if you take the North American continent and the Eurasian, in fact, the Europe plate, and you merge that together with the Greenland up here, you could form and bring all these different lands together. He also notes there was the Appalachian Mountains. Appalachian Mountains, there is a segment on it in the Nordic continent. There are pretty much of the same type, the same types of minerals, the same age, the same everything. So as if this mountain range had been separated by what he called continental drift. Then another observations he did was, if you look at south of South America, south of Africa, south of Australia, and south of India up here, what you find is there are indications of a sediment called moraines. And moraines are sediments that are brought to places by glacial motion. Since these regions currently don't have glaciers, he suggests they were once all connected to the Antarctic continent, and then they moved apart, they drift as a result of this continental drift, this global continental drift. So it's kind of similar to plate tectonics, but it's not the same. And when people ask him, the scientists ask him, what was the driving force or mechanism responsible for that, he didn't have one. He suggested was pretty much the moon, gravitational pull that could be driving that. And the astronomers couldn't reconcile that idea with the knowledge they had of the moon and gravitational forces. And then his idea got to not be embraced until after 1950s and 60s. In fact, he had passed away, and then these ideas start to be retaken and now pretty much confirmed. So the plates do move, and earthquakes and volcanoes are pretty much formed by that motion. Here's an example of a what we call subduction. So when two plates collide, the plate that is denser slides under the plate that is lighter. So here's an example of a continental plate that is colliding with the oceanic plate. The oceanic plate is topped by minerals. They are rich in iron, and the rocks that those minerals make up is pretty much basaltic rocks and gabbro. They are very dense. So although the oceanic plate is thinner than the continental plate, as you can see in the figure, because the continental plate is, the primary rock is granite, which is lighter than basalt, granite ended up floating as it collides with the oceanic plate. So this is the subduction, the example of subduction. And as this subduction occurs, sediments on top of the oceanic plates are brought to very deep levels, and along with water, that helps to reduce the boiling point of the mantle, and that region, asthenosphere, has a name, asthenosphere. That region promotes the transformation of solid rock into liquid rock, and then we have this bubbling up process we call volcanic eruptions. So volcano, an arc of volcano, is generally formed in few hundreds miles away from the region where subduction is taking place. So here in the United States, in the West Coast, in north of California, beginning Mendocino, and going all the way to the Oregon coast. So you have the Juan de Fuca plate. See if I can see. Juan de Fuca plate, this little is a little plate up here that collides with the North American plate, and as a result of it, it formed all the Cascadia range of volcanoes, and some of them are still active. San Andreas is a fault line where the North American plate is pretty much colliding with Pacific plate, and Pacific plate is moving north. And you can't miss the crack on the land. There is a very nice report done. Let me see if I can find now. On that is where the fault lies. Cron 4 report. Okay. This, no, that's not it. Let's see if I can find.
Find something interesting.
I'm taping a lecture. Oh, that's for the online part. What happened when we want to find one thing and we don't find? Oh, there you go. I think I found it.
It's 5:04 at this moment on this day in 19.
No, that's not it. That's not it. Just scroll for. Let's see for the Chrome. That's the one.
Welcome back. I'm science editor Brian Hackney. We're above Point Reyes, but Point Reyes didn't always used to be below us. Point Reyes moved up from where it was formed in Monterey. It's now anchored to West Marin. And those rocks near Palo Alto, they used to be above Santa Cruz.
So this has been transported up here by the San Andreas.
By the San Andreas Fault. That's correct.
This movement happens in one of two ways, so dramatically you'll never forget it, or so slowly that nobody even noticed it until 1956. See, creep on a fault is actually a very rare thing. So let's head south to San Benito County and drink a toast to the place where creep on a fault was first discovered.
So it's a great report, and it shows Calaveras Fault, that we pretty much go through this area where we live, and yes, I will put this in our Canvas course as well, along with this one. So I have two. So San Andreas, if you have some time, you should revisit this Chrome 4. It was aired a few years ago, but it's still pretty much recent. Mountains on Earth are the way they are because of plate tectonics. You cannot find this type of mountains in other planets. If you look at mountains in the Moon or mountains in Mercury or Mars, they are pretty much either volcanoes or impact mountains that were formed as a result of impact. We have an atmosphere divided in different layers, and they respond to temperature in a different way depending on the chemistry in it. Important for our course is the stratosphere, where the excess of oxygen has created a gas called ozone, and which has an important connection with life. The ozone is a gas that is able to block and to absorb ultraviolet radiation, and ultraviolet is an energetic type of radiation that breaks down complex molecules. It has a strong, high penetration power, and so without this protective blanket, some species might not be able to survive or might not even be able to develop. So the ozone is formed in the stratosphere, which is the layer right above the troposphere where we live. Most of the gas, 50% of it, is in the first 5 kilometers in our atmosphere, 3.6 miles or so. Our atmosphere is important because of the hydrological cycle that pumps up erosion and weathering in our planet. So if you look at our planet in comparison with the Moon or Mercury, you look at these places and some of the original craters are still there, especially in the Moon. We had a beautiful full moon yesterday. So why is so different with Earth? Well, Earth has two important factors contributed to the erasure of these craters. One is what we just mentioned, plate tectonics. If you go back to this figure of subduction, what you're really seeing here is any crater that has been created anywhere on Earth, if it's on the route of subduction, in a few million years it's going to be under the ground, and then it's gone. So in a time scale of 100 million years, which is short when you compare with the age of Earth, 4.6 billion years or 4.5 billion years, so all the surface is pretty much redone, except for a few areas called shield areas, which are somehow preserved, and they are made of materials that have been there, since Earth got to receive its very first sediments, pretty much old terrain, 4.2 to 4.3 billion of age. So subduction is responsible for erasing. If you look at the ocean, so the ocean floor is recent. Every time two plates diverge from one another, water fills in the gap. And if you allow this process to go on for hundreds of millions of years, eventually, instead of just sag ponds or lakes, like as you can see in the west, in the east, northeast Africa, eventually you're going to have a sea being formed, and eventually you're going to have an ocean like the Atlantic Ocean is, that separates two continents, Africa and South America, or Europe and North America. So, but basically, so water gets in, and therefore the ocean floor is recent, is less than 300 million years of age. Okay. Stromatolites are a good example of life on Earth in the very early age. So into the first billion years, Earth had life already operating and creating oxygen gas in the atmosphere that quickly got oxidized by rocks. So certain generations of rocks were formed once oxygen started to be dumped as as an element of rejection in the atmosphere. And once these rocks were pretty much satisfied with their oxidation level, then oxygen starts to be accumulated in the atmosphere, and some different living organisms start to making use of it, like we do, and to operate our chemistry. So stromatolites are example of this ancient bacteria that exists and was responsible for oxygen production in our planet. The atmosphere also is responsible for not only providing light and filter out some of damaging radiation for some of us, and I'm talking specifically about the ultraviolet radiation, but the atmosphere also is responsible for giving a reasonable temperature where life can thrive. So if you are in the desert region, the change in temperature between night and day is substantial. Why is that? Well, because in the desert you don't have water, you don't have vapor, and which means and vapor is what our book addresses as a greenhouse gas that is capable of retaining infrared radiation, which is heat, and keep it in the atmosphere itself. So during day and night, the change in temperature is not that severe because the atmosphere has these greenhouse gases. Now, if you get rid of the greenhouse gases, once the radiation hits the ground and some of the minerals process the light and reject the rest, so heat is pretty much reflect off or emit out of our planet and is gone. Now, with the atmosphere, that heat is retained. So greenhouse gases, they have this property of retaining that heat, which is good in a way. Too much of it increase the heat in the atmosphere, which is not a problem if that increase in CO2 production is done over geological period. Like it was if you go back to Precambrian times or even in the Cambrian times, we have our atmosphere with 700 to 1,000 part per million, as opposed to what is now pretty much 400 part per million, which is pretty much less. And if you look at life, especially in the Carboniferous periods, about 700 part per million, life was abundant. The trees were pretty much happy. The bugs were pretty much happy. They were enormous, by the way. And the concentration of carbon dioxide in the atmosphere were pretty much high. And everybody was happy with that. That's okay if, again, you give Earth enough time to adapt to the changes. But when this change occur in a short period of time, going from 350 as it was in 1950 or so, up to 400 in few dozens of years, now we have a big problem because now you have the requirement that not only the atmosphere but living creatures adapt to those changes in a short amount of time, and that can be problematic. This is an example of a crater in Algeria, so it's still there. Cretaceous period, so it's more than 70 million years ago the impact happened. Tunguska is an explosion supposedly happened with an asteroid, a stony rich one, that exploded before hitting the ground. I think there is another one. Yeah, that's the meteor crater in Arizona, and it's 50,000 years ago an impact, Meteor Crater is a nice place to go and visit, and is very well preserved, has a visitor center in there, and is now major impact supposedly happened in about 65 million years ago, and Chicxulub in Yucatan Peninsula has remains, as far as the impacted region is concerned, of this hit. And this hit sent out enough material in the atmosphere that was able to circle the entire planet and causing a change in the weather conditions in a global scale, to the point that big animals couldn't adapt to those changes. A cooling, since the atmosphere got all concentrated with a high concentration of dust, then solar radiation was being reflected back to the space, and then you have a cooling occurring on a very short period of time. Again, cooling is not a problem, but if it's done in short amount of time, when compared with the geological period of time, then life has a hard time to adapt. And then the big guys were gone. So when this hit is measured, so the time that this hit occurred 65 million years ago, when that is compared with the age of the last of the big dinosaurs, that is also were decimated at about 65 million years ago, then geologists just connect the dots. And so dinosaurs were pretty much got extinct because of this collision. Other collisions might happen, yes. According to astronomers, there is a cycle of about 100 million years for a major hit to occur on Earth. The difference is that we have some technology, space technology, that might be used to prevent this hit to happen again. And so there are several projects going on where astronomers try to map the sky and find these leftovers and try to bring ephemeris, precise ephemeris, which means the position where they are, where they're going to be in the future, so that if some of them cause danger to our planet, some plane can be placed so that either is diverged, or this asteroid is, or piece of asteroid is destroyed. Okay. So those are the main points of this week class. And again, be patient with the homework. I might not have the questions matching properly. And I will put the two links on Canvas so you can enjoy yourself. All right. So, Tor, I can hear you still there. Do you have any question? Let me stop taping now so we can talk. Just a second.